I'm going to do an example where we would use the Nernst equation. And this is when we have a cell, and this is our cell notation, that is not under standard conditions. So we are given the concentration of each of the solutions, and it is not 1 molar. So we're not under standard conditions, and the concentration of these solutions will change the reduction potential that is produced. So this is the Nernst equation, and we base the cell potential off of the standard cell potential. And then there is this component based on, so this is a few constants that have to do with temperature, Faraday's constant, but you can use the 0.05916 divided by n, which is the molar value of electrons. So it's the number of electrons being transferred within the equation. And then the log of k, and that k is the equilibrium constant based on your solution concentrations. It's given a little asterisk there because it's more representative as Q, because the solution is not necessarily at equilibrium. Let's write out our half reactions here. This is our anode, because of the cell notation is anode cathode. So we have oxidation occurring at the anode, and we're going to have zinc going to the zinc 2 plus 2 electrons, and you're going to have silver plus 1 electron going to solid silver at the cathode. This will have to happen 2 times to have the chemical equation balanced. So we right away we know that our N value, I'm going to change colors because it just dropped red. Our N value is 2. Okay. Now we can also calculate the standard reduction potential by looking at our value. So the standard of the silver reaction is 0.80 volts. 0.80 volts, and the standard reduction potential of the zinc reaction is 0.76 volts, and we're going to flip it so that the negative 0.76 becomes 0.76, and this is written as oxidation. So I'm going to actually write it there, the E of ox versus E reduction, and do the E naught equation where we're adding the oxidation and the reduction reactions. I've already flipped this. This will be 0.80 plus 0.76, giving 1.56 volts as our standard cell potential. You would get the exact same equation if you did cathode minus anode, because it would be 0.8 minus negative 0.76. These values can always be found in your standard reduction standard reduction potential table of values. The K is the concentration of products over reactants. Now, silver product is a solid, so it does not have a concentration. So you're going to have the concentration of zinc over the concentration of silver, because, again, the zinc solid doesn't have a concentration, just the silver ions. But note, we're going to times this whole equation by 2, so that there's a 2 in front of all of these, and our electrons cancel out. When we did the equilibrium, you always had to have that coefficient as an exponent, and that is the case here as well. So your K value here is going to be zinc's 0.001 over 0.1 squared, and that K value is just 0.10. We now have the 3 variables to plug into our Nernst equation which will give us the cell potential under not standard conditions. Just the cell potential is what we'll label it. That'll be 1.56 minus 0.05916 over 2 log 0.10. Becomes 1.56 minus negative 0.0295, which will give us 1.59 volts when we give our final answer under the proper significant figures. So that's an example using the Nernst equation, which you would need to use if you have a cell that is not under standard conditions. And usually what we're going to look at is cells where the solutions are not exactly 1 molar.